Welcome to the Bradford seminar series. I'm Denise Malbrough. I'm a professor joint between C-PREE and the Center for Policy Research on Energy and Environment and the Civil and Environmental Engineering Department. And today I'm particularly delighted and honored to introduce Professor Daniel Jacob from Harvard. Daniel was my PhD advisor many years ago, and I was his second doctoral student.
And Larry was my first.
Larry's here with Larry. Since then, he's gone on to dominate the field of atmospheric chemistry with his former doctoral students populating faculty positions around the world. Over the past couple of years, I've started receiving emails saying that I'm now among the top 1,000 environmental scientists in the world, and out of curiosity, I went to look at this list to see who was at the top. And I discovered that Daniel Jacob is #1 in the United States and #1 in the world in terms of environmental sciences, publications, and citations. Since receiving his PhD at Caltech and starting at Harvard as a postdoc back in 1985, his list of honors and professional accomplishments has been long and illustrious. To mention just a few, he recently received a special commendation for extraordinary teaching during COVID from Harvard. At the start of his career, he received the Packard Fellowship for Science and Engineering and the Presidential Young Investigator Award. He's led the development of the GS-10 three-dimensional atmospheric chemistry model, which is now widely used around the world. And he served as mission scientist on 8 NASA aircraft missions around the world and as a member of several satellite science research teams. When I was Daniel's student, I was really interested in the critical role that scientists could play in informing environmental policy. And at the time, Daniel was more interested in really understanding the fundamentals of what was happening in the atmosphere. He had this magical ability to get everyone super excited about crazy atmospheric reactions that were occurring. Where did this pollution come from? Where did it go? What happened to it in the environment? I'm happy to report that since then he's become more interested in the connection between science and policy. And he's here today to tell us about mapping methane emissions from satellites, which is a critical tool for being able to determine whether and how well the world succeeds in meeting the global methane pledge to reduce global methane by at least 30% from 2020 levels by 2030. And satellites provide the ability to both see what has been emitted in the past and to see how emissions are changing. Reducing methane emissions is the single most effective way to slow climate warming in the immediate term, and satellite data allows scientists to act potentially as atmospheric police, identifying where the largest emissions come from, how they change over time, and potentially being able to hold large emitters accountable. Again, we look forward to hearing more about methane in the climate system.
Thank you very much. Thank you. Denise, thank you so much for this very kind introduction. And yes, I've enjoyed my time here immensely, learning about the science policy interface from all of Denise's students and the challenges in arriving at climate solutions. And I look forward to meeting with several of you this afternoon. So I'm going to talk today about the role of methane in the climate picture and what we can do from satellites about better understanding the methane budget and enabling climate action. And all this work is not done by me, but by my brilliant army of students and postdocs, including Nick Belesis, who's a second-year PhD student, Zishang Shen, who's a postdoc, Xiaolu, who's now a professor at Sun Yat-sen University, Hannah Nesser, who just graduated last Friday, Jen Chu, who's now a professor at North Carolina State, Tia Scarpelli, who works at Carbon Mapper, Lu Shen, who's a professor at PKU, and I don't need to introduce Daniel Varan, who has been at home in Princeton for a couple of years. Okay, so we're motivated by the need to curb rising atmospheric methane. So methane has tripled in the atmosphere since pre-industrial times. We know this from ice cores. We've had direct measurements of methane in the atmosphere continuously since the 1980s from NOAA and other agencies. And when we look at this continued growth over the past several decades, you see that it's by fits and starts. So in the early 2000s, the methane was flattening and it appeared to reach some kind of steady state, and we're wondering why that was. But then in 2006, it started to increase again, And then this growth has accelerated over the past decade. And the three more recent years, 2020 to 2022, have seen the sharpest rise of methane in the record so far. Now, methane, unlike CO2, comes from a pretty big array of different sources. In the case of CO2, we know it's all fossil fuel combustion, and we see this majestic rise. But in the case of methane, it's more complicated than that. So methane is produced biogenically by microorganisms operating in environments without any oxygen, so-called anaerobic environments. And this is responsible for the largest natural methane source, which is from wetlands. Now, we also have anthropogenic sources that produce methane biogenically. We have rice paddies, which are essentially artificial wetlands. We have landfills, wastewater treatment plants, and livestock, including both ruminants, but also the management of manure. Now, in addition to that, we have methane produced what we call thermogenically at very high conditions of temperature and pressure in sediments. And this is what gives us our fossil fuels, and in particular, our natural gas. So when we exploit our fossil fuels, either through the oil and gas infrastructure or by digging for coal in coal mines, there's a lot of methane that's generated and that may be vented to the atmosphere. So when we look at this ensemble of sources, we can kind of rationalize the tripling of methane since pre-industrial times by the fact that natural sources account for about 1/3 and anthropogenic sources account for about 2/3. But you see, first of all, that there's a large amount of uncertainty in these individual sources, and also that the anthropogenic sources are quite diversified. So the way we estimate emissions traditionally, and this is what is shown in this pie chart, is by a so-called bottom-up approach, in which we infer emissions by multiplying some activity rate, say, for example, the number of cows, by an emission factor, the amount of methane emitted per cow. And there's a large uncertainty associated with these kind of estimates because the methane is either produced through biological processes, which are always complicated to model, and then the methane that's actually emitted to the atmosphere from these biological processes is a small residual between methane generation and methane consumption. And then in the case of the fossil fuel infrastructure, we had a lot of methane that's associated with leaks or with poor management of operations. And again, this is very difficult to quantify. Now, methane in the atmosphere has a lifetime of about 9 years against mostly oxidation by the OH radical. And that makes it a pretty short-lived greenhouse gas. And as we will see, this is going to be quite important in terms of its implications for climate. Now, methane has recently become of great interest to climate policy, unless you've been living in a cave. I'm sure you've noticed this. And I'll let Joe Biden talk about it, if we can get better sound. Okay, we can't hear him, so I'll stop it. Oops. Okay, well, it doesn't matter. He can talk. But sometimes this happens, and so I have here the important points that he makes. 3 very important points. So first, one of the most important things we can do to keep 1.5 degrees in danger in reach is to reduce methane emissions as quickly as possible. That's point number 1. Point number 2, methane accounts for half of the warming that we've experienced so far, and he repeats half, so he's doubly wrong. And then the third thing is he's announcing the global methane pledge to reduce our collective methane emissions from all the signers of global methane pledge, which are 111 countries, by 30% by 2030. And he bravely says that I think we can go beyond that. So I'm going to unpack a little bit those 3 points. So the first thing is, how did he get to say that methane is responsible for half of the warming? I mean, what about CO2? Well, he should have said a third. So what I'm showing you on the left here is from the latest IPCC AR6. This is actually Vishalinek's chapter, showing the radiative forcing from different climate agents reference to their emissions. You're probably familiar with this bar chart. It basically looks at the contributions from different agents to disrupting climate equilibrium. So you have warming if it's positive, and you have cooling if it's negative. And the latest IPCC decided that nobody understood radiative forcing, so they would have to translate it into a change in the surface average temperature as a result of these individual agents. And it's basically a multiplicative factor, so it's not very creative. But the point is that if you look at the observed warming of about 1.1, 1.2 degrees Celsius, and you compare it to the warming associated with methane, which is 0.6 degrees Celsius, you deduce that methane is responsible for half of the warming. But that's, of course, silly fallacious, because it doesn't account for the cooling effect associated with the aerosols. So the cooling effect of the aerosols offsets part of the warming, and so it would be much fairer to say that CO2 accounts for half of the warming, methane for 30%, and 20% is from the other greenhouse gases. All right, so CO2 is still the king of global warming. Methane is not half. Nevertheless, methane is quite a big deal. 30% is nothing to spit at. But the fact that it's been responsible for 30% of the warming we've seen so far really doesn't necessarily translate into the emission controls that we should be applying for the future. It doesn't mean that we should just eliminate methane emissions, and as a result, our warming would reduce by 30%, because it's all wrapped up in the lifetime of methane. So methane, as I told you, has a lifetime of 9 years. And this is, again, from Vishalinek's chapter in the latest IPCC. And it shows the response to 1 year of present-day emissions for CO2 and for methane after 10 years and after 100 years. So if I emit both methane and CO2, after 10 years, what happens? Well, methane is still in the atmosphere, and it has, a very strong radiative forcing efficiency. Molecule per molecule, it's much more efficient than CO2. And so even though you have 200 times less methane than CO2 in the atmosphere, you see that it actually is more important than CO2 in driving the temperature change after 10 years. But after 100 years, methane is gone. CO2 is still there. The warming that you had from methane is gone because it's been radiated out to space. And so when you look at a 100-year horizon, it's all about CO2. So we got to be very careful about distinguishing the climate effects of methane and CO2. They are not equivalent, even though in climate policy they are considered as equivalent. This is actually, it should not be that way at all. One thing for sure is that reducing methane emissions now would have a fast impact on climate. So considering that we're dealing with climate change, both right now as an immediate pressing problem, as well as a long-term problem, that means that we should have a strategy for reducing both methane for near-term impacts and CO2 for longer-term impacts. And in particular, acting now to stave off near-term impacts could save us from climate tipping points. And in that regard, 1.5 or 2 degrees of dangers, but I probably don't need to tell you that, is actually a very serious metric. Beyond that, you run the risk of switching to kind of very different climate, abrupt climate change. We definitely don't want to do that. But another thing, and one thing that's not generally brought to the table, is that controlling methane offers a unique opportunity to go after ozone pollution. So methane is a precursor of ground level ozone, which is one of the two main air pollutants, the other one being PM2.5. And because of its long lifetime, it affects ozone globally. So if you reduce methane emissions, you will bring down ozone by a non-insignificant amount throughout the world. Controlling methane has not been on the radar screen of air quality agencies because they are entrusted in ozone in their particular jurisdiction. There is no global treaty for ozone pollution. And so really the only way that we would go after this source of ground level of ozone for methane would be through climate action. But this is a very important co-benefit, and if you measure it in terms of dollars and in terms of lives saved, it actually makes a big difference. All right, so methane should not be viewed as equivalent as CO2, but I want to view it more as a stopgap for immediate climate action while we decrease CO2 emissions and develop carbon capture technology. So in this conceptual diagram that I stole from my faculty colleague David Keefe, and I'll get into that in just a minute, I'm showing you climate risks versus time. And so in the business as usual scenario, we blissfully cross 1.5, 2 degrees of dangers, and eventually we get into serious trouble. So we don't want that, and we start climate action. But starting climate action in terms of CO2 emission controls is going to take time, as you know, and eventually we want to get to net zero for CO2 emission. But even if we go to net zero CO2 emission, it takes a long time for CO2 to be removed from the atmosphere. Lifetime is complicated, but it's a few hundred years. And as a result, we'll be in a sustained regime of warming and a sustained regime of increased risk of climate tipping points. All right, so it's becoming increasingly realized that we can't just go to net zero. We actually have to remove CO2 from the atmosphere. And we definitely don't have the technology yet to do that on a mass scale, but that is actively being worked on. And so we can hope, therefore, that maybe within a few decades, we'll have a technology developed in order not only to decrease the CO2 emissions to net zero, but to capture CO2 from the air. Okay, but that is still likely to get us above 1.5 or 2 degrees of danger. So a way to try to avoid reaching this peak here is by going after methane emissions. If we can go after methane emissions now, then we can stave off this maximum. We can get below the maximum level of climate risk and go faster along this curve of decreasing greenhouse warming. All right. Now, this is, like I said, this is a slide originally from David Keefe. I fiddled with it. But as some of you may know, David is a big advocate of solar geoengineering. He would not like to be called an advocate, but he certainly has put solar geoengineering on the radar screen, putting a lot of particles in the stratosphere in order to reflect solar radiation out to space and therefore offset the effect of greenhouse warming. And what he had here, instead of methane emission decrease, he had solar geoengineering. And what I'm saying is that if you like solar engineering, you'll love methane emission decrease because it's going to do exactly the same thing, except it's not going to be messing around with the atmosphere, and solar geoengineering is not a good idea for all kinds of reasons. But methane emission decrease is certainly not objectionable. In particular, it really should be easy, because simple measures can go a long way to decrease emissions. So, fix leaks from pipelines or from, oil and gas infrastructure. If you can't handle the methane that you generate from oil production, well, flare it. Or even better, figure out a way to use it. What we call associated gas. Recover the gas from landfills. Put it digesters from manure ponds, wastewater plants, converting methane to CO2. Changing cattle feed, maybe changing cattle breed, maybe telling people to eat less meat. But okay. Certainly going to different modes of rice cultivation. all of these take some doing, but they're nothing like trying to get away from CO2. And unlike for CO2, there's no stockage problem. You don't have to worry about where you put all of this carbon. Oh, you convert it to CO2. But it's only a very small fraction of CO2 compared to direct emission. Again, methane, molecule per molecule, is a far more efficient reinforcing agent. All right, so this would seem to be easy. And this is why Joe Biden says, you know, yeah, 30% by 2030, and we think we can do better than that. But the problem is that methane is coming from a zillion of individually small point sources. And those point sources have highly variable emissions. And at any point in time, you know, one of these devices could be leaking, venting, or the flare gun out and releasing massive amounts of methane. And this is very difficult to police. This is very difficult to observe. And this translates into very large uncertainties in our methane emission inventories that are built to provide information for climate policy analysts. So this is work from my former student T.S. Garpelli, in which she constructed a new bottom-up emission inventory for oil and gas worldwide, and she compared to other bottom-up inventories. And you see that depending on the country, you have huge uncertainties. This is a log scale. Okay, so basically with this kind of variability that reflects mostly uncertainty in emission factors and leak rates and management practices, there's really very little policy that you can do. And so it's all well and good for the Paris Agreement to say that we're going to do a global stocktake of greenhouse gas emissions, and on that basis, we're going to come up with nationally determined contributions and all of that. All of that is based on those bottom-up inventories that really don't have a whole lot of credibility. Okay, so this is where I come in. All right, atmospheric methane observations can improve this situation. The atmosphere doesn't lie. If I see elevated methane somewhere in the atmosphere, well, I know there's a source nearby. Okay, don't tell me otherwise. Okay, but how do I do this formally? Well, what I'm going to do is I'm going to start from one of those bottom-up inventories, and what I'm showing you here, just for the sake of illustration, is Texas and New Mexico within the Permian Basin that straddles Texas and New Mexico, and we'll go back to the Permian later on. And so, okay, so we have this bottom-up inventory, and this particular one is from EPA, and then we say, okay, how can we improve it? Well, we're going to improve it by observing methane concentrations in the atmosphere. And we can do this from surface sites, we can do this from aircraft, and we can do this from satellites. And satellites have a big advantage that they provide continuous coverage in both space and time. And they observe globally. No country can hide from satellite observations. So this is why I'm going to focus on satellites. Now, the way that we're going to use that information in order to improve the bottom-up inventories involves a little bit of mathematics that we're not going to go through. But what we do is we start by taking this emission inventory and combining it with an atmospheric transport model to predict concentrations. And the reason for this is because the observations are of concentrations. But what we want to know are the emissions that drive these concentrations. Okay. Now, with a physical model, like an atmospheric transport model, the kind of models that Larry works with at GFDL and others, what you do is you predict concentrations on the basis of emissions. That's called the forward problem. Okay. But what we want to do is the reverse, infer the emissions from the observed concentration. And that's what's called an inverse problem. And so in this inversion, which involves some statistical optimizations, we correct the bottom-up inventory. We come up with what we call in our jargon a posterior emission estimate. And that posterior estimate improves on the prior bottom-up estimate by adding the information from the atmospheric observations. Okay? And that's an important point, is that there's no opposition, there's no incompatibility between the top-down information that you get from the atmospheric observations and the bottom-up inventories. They're actually complementary. The atmospheric observations gives you additional information with which you can improve the bottom-up. Okay, so we have an armada of satellite instruments now in space or scheduled for launch within the next few years. And we'll be talking about observations involving several of those instruments. All of these instruments measure methane by solar backscatter in the shortwave infrared. So here's basically how the technique works. With a satellite, you look down at the surface and you pick up reflected solar radiation in bands where methane absorbs. And so by looking at the attenuation of a reflected signal, you infer how much methane you have in the atmosphere. This is a column measurement. You measure the total amount of methane in the column. So you have to interpret it carefully. The one wonderful thing about the shortwave infrared, we're talking about 1.6 micron or 2.3 microns, those are the two major absorption bands, is that the atmosphere is largely transparent in that part of the spectrum, unless you have clouds. If you have clouds, you're not be able to see anything. But clouds aside, you're able to go all the way down to the surface. And so therefore, if you have methane emissions at the surface, increasing methane concentration there, you'll be able to pick it up from the satellite. Okay, the satellite instruments that we have presently in space or scheduled for launch soon can be put into two broad categories in terms of the very different measurements that they provide. One is the area flux mappers. Those are the instruments that will measure the total amount of methane, and they will do this typically globally. And they will be designed to observe methane, so which means they have very high spectral resolution, and so they can deliver very high precision so that you can measure the methane concentrations accurately. You pay the price in terms of pixel resolution, the spatial resolution that you get your information, and so these instruments will have a pixel size of typically a few kilometers. A very different type of instrument are the point source imagers. So point source imagers are instruments that can observe individual plumes of methane emanating from point sources. In order to do that, they have to have very fine pixels, and they pay for that with having coarse precision. But that's okay, as long as you just want to see a hot point source, a very high point source. You don't need to have very high precision. You just want to see a large enhancement relative to the background. And there's been a whole cottage industry of these point source imager instruments because, well, first of all, because of the interest in observing point sources, and this was really started by Daniel Varon, who was my student at the time, and we worked with GHGSat, a Canadian company, to develop this kind of technology, but also by the discovery that instruments that are not intended really to observe methane, think instruments like Landsat that are just designed to observe land surfaces, in fact can provide information on methane if the point source is sufficiently high. And again, Daniel Varon has been doing some pioneering work on this. So I'm mostly going to talk today about the information that we can get from the area flux mappers, because here we're more about talking about climate policy at the national or global level. I just have one slide on, oops, actually, before I get into that. So between this ensemble of instruments, we have in the satellite system, actually, since I said I would have one slide on this, this is my slide on point source observations from space, and this is a paper from Daniel Varon that was published a few years ago, and this was the first time that we observed large point sources from space in a continuous way. And this was a microsatellite from GHGSat, observing with 25 by 25 meter square pixels, and we saw these huge point sources in Turkmenistan. And since then, there's been a lot of observations of point sources like this all over the world. One big surprise is how intermittent they are. Sometimes they're persistent, like this one from a compressor station that we saw all the time for over a year. And then there's some that we only see once, you know, and never to see again. So like just a single burp of methane. Okay, but as I was saying, with satellites, we cover a continuum of scales to enable climate action. So on the global scale, the big question that we're trying to address is attributing the increase of methane. Why is methane increasing in the atmosphere, and why has this growth been accelerating? Another thing that we can do with global methane observations is to understand the variability of OH, the main atmospheric oxidant, but this is not something I'm going to talk about today. Okay, on a smaller scale, on a regional national scale, we can quantify emissions contributed by individual countries to the UNFCCC for purpose of a Paris Agreement, and in this way contribute to climate policy, improve bottom-up inventories, and we can also do this on a regional scale. And then at the level of point sources, we can detect large point sources in a way that can enable quick climate action. When we see large plume, like I showed you for Turkmenistan, we can contact the operators and tell them, hey, you're leaking methane like crazy, can you do something about it? It's hard to do in Turkmenistan, which is something like North Korea, but we eventually managed to do it through the Canadian diplomatic mission. Okay, so what I'm going to do is first talk a little bit about the global budget of methane and why is methane increasing and what are the contributions from individual countries, and then we'll zoom in more to the national and regional inventory. So what I'm showing you here is observations from the GOSAT satellite instrument that was launched by JAXA, that's a Japanese NASA, back in 2009. And it's a very high quality instrument that's been providing us with continuous measurements of methane now for 15 years. And the only problem is that it's relatively sparse. It only observes 1 pixel every 250 kilometers or so, but that still gives you plenty of data. So what I'm showing you here is the methane concentrations observed by GOSAT over, I think this is 2010 to 2015. Basically you see high values in China, India, high values in the tropics, and we'll get back to that. So one of the first things we did when we started to use satellite observations was to use the GOSAT data to do an inversion of global methane sources and figure out the contributions from individual sector. And this is what I'm showing you here in the bottom. And one thing that this revealed is the important role of tropical livestock in terms of contributing to total methane emissions. We also found that wetland emissions were quite a bit lower than what we have in the current bottom-up inventories. With GOSAT, we came up with a list of all the countries in the world and how much methane they emit. And my colleagues at the government, at the Kennedy School of Government are really lapping that up. They really like that kind of stuff. What I'm showing you here is just the top 10 countries. Okay, so you see China is the number 1, India is the number 2, the US is the number 3, and then it starts going down. You see that almost all countries have an important contribution from livestock. Beyond that, it varies a lot depending on the country. So for example, China has a very large emission associated with coal. The US is the number 1 emitter from the oil and gas sector. And so on. I mean, this top 10 list does not, beyond China, India, and the US, those are not really countries that you typically associate with a lot of fossil fuel combustion, like bad actors for CO2. And that's because methane is a very different kind of problem. Rather problematically, 5 of those top 10 countries, including the top 2, have not signed the Global Methane Pledge. Global Methane Pledge has been signed by 111 countries, but those big emitters have refrained. Okay, so with GOSAT operating for the past, since 2009, we can infer the global emission trend of methane and attribute it to specific location and sources. So this is work from my former postdoc, Jen Shu. It's in preparation. I don't want to talk too much about it, but what we are doing is we're trying to reproduce the trend in methane that's observed at the NOAA stations. I showed you this before by GOSAT. And so to do that, we have to correct the emissions of methane. And when we do, we can very closely reproduce the trend observed by GOSAT. And then we can figure out from the inversion where methane emissions are increasing and where they are decreasing. And what you see is that most of the increase is really coming from the tropics and associated with biogenic sources, including wetlands, including livestock, and I think including rice. But we need to do a little bit more work on this. But Africa right now is developing a lot of rice agriculture, and I think this could be contributing to the increase of methane. I'm also very interested in what's happening in Indonesia. Indonesia has a lot of, it's the third biggest coal producer in the world, and yet they report extremely low coal emissions to the UNFCCC. So I want to check this out. It's a difficult place to observe from satellite because there's so many clouds and also land-ocean contrast, but we're working on it. Okay, so an important point actually is that the increase, again, is mostly from the tropics, mostly appears to be biogenic. I don't think that oil and gas in North America or Europe contributes much to the increase at all. Even though it is an important contribution to the global budget, and so one that we can act on, it's not one that's contributing to the increase. Okay, so GOSAT, as I told you, has a problem of being relatively sparse. Since 2018, we have had in space the TROPOME satellite instrument that was launched by the European Space Agency. It's a Dutch instrument, and that instrument provides global daily coverage with very high precision. It's not quite as nice an instrument as GOSAT, and it requires quite a bit of cleaning up. Satellite observations are really hard to work with, and you have to do a lot of what we call data cleaning. This is work from my student Nick Balassis in terms of generating a cleaned up product of TROPOME observations. And this is 2021. So, you know, what do you see? You see the highest concentrations, really therefore the highest emissions in the tropics. This is actually the Sud wetlands right here in Africa. This is probably wetlands, but also oil and gas in Nigeria. You see Venezuela, you see the Indo-Gangetic Plain, you see the East China Plain. Okay, so we've been using TROPOME to do inversions with higher resolution than we previously could do with GOSAT, and on that basis come up with methane emission inventories informed by the satellite observations for all of the countries in the world. Well, we're tiling the world right now. I'm showing you here a paper from my postdoc Zishang Chen. It's actually in press. It should be published very soon. And it's focusing on the Middle East and North Africa. Middle East and North Africa is a region that's of particular interest, of course, in terms of oil and gas. So we're looking at 23 countries in that region, and we provide emissions for all of these countries. And again, we're doing this now all around the world. But let me show you a few interesting things about this Middle East and North Africa study. What I'm showing you here on the top is the production of oil, okay, and then on the right here is the emission. And the bottom is the same thing for gas, okay, and it's arranged in order of decreasing production, okay. And what you see is that the production, the countries that are large oil or gas producers are not the ones that are large emitters. There's actually no correlation at all between the two. Now, you know, if you're a climate, if you're a climate policy guy and you have to submit your inventory to the UNFCCC, and you go to the IPCC for guidelines on how you could construct your inventory, what they will tell you is that you should apply an emission factor to a unit of oil production or to a unit of gas production. And what we find is that this is completely flawed because there's in fact no correlation between the two. And so we've looked at other metrics to compare emissions between countries, like the number of wells, the number of new wells. We had little success. And what that means really is that infrastructure and management are what drives the variability between countries. Now, one way to quantify this is with the notion of methane intensity. Now, methane intensity, I think, was introduced by the Environmental Defense Fund about 10 years ago as a concept, but it's been embraced by industry since then. And it measures the amount of methane that you emit from the oil gas sector per unit of methane production that you deliver to the market. In other words, how much methane are you emitting that you could instead have delivered to market and use for fuel, used as fuel. So the industry has stated a target of 0.2%. They say we're presently at 0.3%, and we're going to go to 0.2% as part of the Global Methane Pledge. Okay, this is from the Oil and Gas Climate Initiative, which is a consortium of oil and gas companies. Well, when we calculate the methane intensities from the individual countries in the Middle East and North Africa, and here I put in the US for good measure, what we find is methane intensities that are considerably higher on average than this objective from the oil and gas industry. Okay, in the US, it's about 2.5%. You have some countries that are totally crazy, Iraq approaching 20%. But perhaps most interestingly is that you have some countries that actually meet that objective and go beyond that. Kuwait, Saudi Arabia, and Qatar have extremely clean operations. We can see that from space. And we think that's due to three reasons. The first one is that they have very concentrated infrastructure. Whereas in a typical oil gas field in the United States, we'll have 10,000 wells and associated piece of equipment, gathering pipelines, gathering stations, storage tanks, and so on. In those countries, they only have a relatively small number of highly producing wells. Their infrastructure is also very modern, and they are committed to using the natural gas rather than venting it. So if we were to achieve this 0.2% target for all the other countries, we would decrease oil and gas emissions by 90%, basically making oil and gas an irrelevant player in terms of methane emissions. And we would be well on our way to meeting the goal of the Global Methane Pledge. Okay, so this was for the Middle East and North Africa. We've also been focusing on fuel, oil, gas, and coal, on tiling the world, looking at all the different regions where we have significant oil, gas, or coal production. And so what I'm showing you here on the top are the emission inventories reported to the UNFCCC, and then on the bottom are correction factors. And you see correction factors can be really high in places like Russia. When we look at global emissions, we find that oil and gas emission is 30% higher than what is reported to the UNFCCC, whereas coal emission is much better quantified. Coal emission is easier to quantify because it's associated with large coal mine vents. Often the methane in those vents is directly monitored. In any case, it's a relatively small number of sources. So coal is okay, but oil and gas is very uncertain. What we see is that the underestimate is driven by the top 4 countries, US, Russia, Venezuela, and Turkmenistan, that emit methane from the oil and gas sector. So we've zoomed a little bit more over the US and looked at what has been the trend in the methane intensity. In other words, have things been getting better? And so again, Here we look at the GOSAT satellite instrument because it allows us to go back to 2010. And this is a paper from my former postdoc, Chalou, that just got published and got quite a bit of media attention. But what we find is that emissions from oil and gas emission over the past decade in the US have been pretty flat. They've been pretty flat even though oil and gas production has doubled. Okay? There's been a period between 2014 and 2017 where emissions have actually gone down, and we associate this with a decrease in the drilling of new wells. Most of the methane emissions associated with wells come from the first year of operation, which is called the well completion. And beyond that, the emissions really drop. So when we look at the methane intensity trend between 2010 and 2019, we see that there's been a national decrease from 3.7% to 2.5%. And perhaps most importantly is that the variability of the intensity between regions has greatly narrowed. So it used to be at the beginning of the past decade that we would have huge emissions from the Permian, huge emissions from the Bakken right here, and these two basins seem to have really cleaned up their act. Okay, now 2.5%, we are still much larger than the industry target of 0.2%, but that presents an opportunity. Because we say, okay, well, we can say to the oil and gas industry, you say you can get to 0.2%, and by the way, we've checked it out. Yes, you can get to 0.2% if you behave like Saudi Arabia or Kuwait or Qatar. Okay, so now let's work towards this, and let's keep on decreasing emissions. Okay, now another thing that we want to do is to be able to monitor emissions with high temporal frequency, so that we can better inform climate action. And this is work from Daniel Varon, looking at emissions in the Permian Basin that I showed you before from week to week, using the TROPOME observations and going from 2018 to October 2020. And you see quite a bit of variability from week to week. And Daniel has been able to relate this to different forcing variables. It's not easy, and some of those wiggles are pretty uncertain as to where they come from, but it seems that new well drilling seems to be associated with spike in emissions. When we increase takeaway capacity, that is the capability to handle the gas associated with oil production, then emissions will drop. If we have a crash in gas prices, I think there the prices went negative, then the emissions will go up. An important thing is that during this period, there was a 50% increase in oil production and a 100% increase in gas production, and you don't see an increase in emissions. In fact, it could be related to the 100% increase in gas production, because instead of emitting the gas, you're actually taking it to market. But this is definitely hopeful in terms of being able to reduce emissions in the future. Okay, this is work from my PhD student, Hannah Nesser. She just defended last Friday. She presented this. She's been exploiting the TROPOME observations to look at emissions over the United States with very high resolutions, 25-kilometer resolution nationwide. She actually did it for all of North America, but she found that she could only get really good information for the United States. So for the United States, with this kind of analysis, you can get patterns of increases and decreases relative to the EPA inventory. You can find where the EPA inventory is too high. You can find, that would be mostly in the coal country. You find places where it is too low, and then you can aggregate this and come up with some national estimates separated by sectors. And the thing that's most spectacular here is the large underestimate of landfill emissions. And landfills have kind of been under the radar screen, as researchers have tended to focus on the oil and gas sector as a place where we could have easy action. But it turns out that the emission estimates from landfills that are reported mostly by the individual landfills to EPA are quite a bit too low. And Hannah finds that this is because of three factors. The first one is that they overestimate gas recovery. Landfills that have systems for gas recovery in place typically report 90% recovery of the gas, and what we find is that it's more like 50%. There's an overestimated decay rate of emissions. So there's a notion that when you put waste in a landfill, during the first year it's going to emit a lot of methane, and then you have a first order decrease. But we find that methane keeps on getting emitted, and we see that by looking at landfills that have recently closed, and we see that they're still emitting methane just like before. And then, of course, site-specific operating practices. The analysis of Hannah also allows her to zoom into emissions at the scale of individual states and urban areas. And this is something that I've learned from my colleagues at the Kennedy School, is that you shouldn't just talk to EPA. You should be talking to the state agencies, you should be talking to the cities, because they actually have a lot of resources to actually enact climate policy on their scale. So with the high resolution that Hannah was able to achieve, we can come up with emission inventories for all 48 states of the contiguous US. And what I'm showing you here is a top 10. And Texas is actually responsible for over 20% of emissions in the United States, and that's mostly because of oil and gas production, and in fact mostly because of the Permian Basin, which is the largest oil field in the United States. But you see that depending on the state's livestock and landfills are also very important players. So we did the same thing with 93 different urban areas, and what I'm showing you here again are the top 10 in terms of the methane emitters. And there at the level of cities, the important players are landfills, gas distribution, and wastewater plants. And actually, just a couple of days ago on Saturday, there was an article in the Boston Globe about Mayor Wu, our new mayor in Boston, announcing expansion of Boston's food waste curbside collection program. So if we can compost our waste rather than sending it to landfills, we'll emit CO2, but that's not nearly as bad as emitting methane. Okay, I think I'm almost done. And when did we start? Do I have a couple minutes, or should I?
Well, we probably end at 1:15, so it's 1:07.
Oh, okay. All right, so I'm just going to take a couple minutes to tell you about a tool that was developed by Daniel Varon and a couple of other people in my group, and we're very excited about this. And it gives stakeholders the ability to do their own inversions on the AWS cloud in a way that's totally transparent and uses our best methods for optimizing methane emissions. So all the work that I show you in terms of inversions is pretty complicated. You got to work with satellite observations, there's some pretty fancy mathematics, but you don't need to understand all of this in order to be able to take satellite observations and quantify emissions in your particular area and their trend. So what we do is we take the satellite data that's resident on the cloud. We also take data from point source imagers, giving us individually large point sources. And we take our inversion code that's ported on the cloud. And out of this, and with a user-friendly interface, we allow stakeholders to generate their own top-down emissions. Okay, and this is actually now being incorporated in the NASA Earth Information System Initiative and also in the IMEO, the International Methane Earth Observations, which is from the United Nations. It's still a prototype, but we're very excited about this because it gives the users a way to do their own analysis of methane emissions. And also for us, when we report results, our code is totally transparent and our results are totally reproducible. So let me give you an example. For the Permian Basin. So this is a Permian Basin right here, and our user wants to do an inversion for this particular region for a month. So what they will do is they will start what we call the preview, the IMI preview, in which we're going to tell you how much data we have. We're going to tell you how much information content you can expect. We're going to tell you if there's anything weird that appears with the data. And at that point, you really haven't shelled any money. Okay, there's no money really involved, maybe a couple dimes. Now, if you say, okay, this looks good, I'm going to do my inversion, then we do the inversion with the methods that we use in our research applications, and out of this, we'll give you the posterior emissions, and we'll give you the level of information that you can get, what we call the averaging kernel sensitivities, and a 1 month inversion will set you back $20. So it's really not that bad. All right, so this is really our vision to enable stakeholders to infer greenhouse gas fluxes with an easy-to-use cutting-edge inversion capability, bringing compute to data, and that's my takeaways. And with this, I want to thank you very much for your attention.
Thank you so much for that useful and inspiring talk. We have time for a few questions. Thank
you, Daniel. Very interesting talk. Your slide showed that during the past decades, the increasing trend of methane mostly focused on concentrating on the tropical region from, if I remember correctly,
Right.
land and livestock. And what are the driving factors of the increasing emissions from these sectors, and how could all the possible mitigation from anthropogenic sources compensate these changes or other climate change-induced increase in methane that we are probably not able to mitigate?
Yeah, thank you. This is a very good question. So in the case of wetlands, we're not sure why the emissions are increasing. There's indication that higher inundation is a reason, in particular in Africa, where we have focused our analysis. The past few years, I've seen a lot of inundation in wetland areas. So expanding the area occupied by wetlands, which is a principal driver for emission in tropical wetlands. It's inundation. Now, whether that represents a response to climate change is not clear. I certainly hope it doesn't, and that it just represents variability, but time is going to tell. In terms of livestock, we know that tropical livestock has increased a lot in the tropics as those populations depend increasingly on a meat-based diet. And then the rice. The rice is something I'm really interested about right now because China is playing an increasing role in Africa in providing advice for development. And one big piece of advice is say you should be growing rice. and in Africa, they used to grow a lot of upland rice, so without flooding of rice paddies. And it seems like the Chinese are saying, no, that's not the way to do it. And so flood the rice paddies, and as a result, you generate a lot of methane.
Last AR6, and I wonder if you could explain the relationship, because if lower methane would reduce ozone, is that being factored in? And my second question, just if you answer both, is I was curious how you were able to separate out the sources of methane so clearly between livestock and other sources, where at least for some of the land uses, they're kind of intermingled.
Right, thank you. So with regard to the first question, it's now been a couple of IPCC reports that radiative forcing has been reported on an emission basis. That is not simply looking at the increase in concentration since pre-industrial times, but looking at the effect of emissions relative to the natural state. And so methane being a precursor for ozone, and ozone being a greenhouse gas, means that when you have methane emission, you will have a component of a warming that will be associated with ozone. If you were to do a radiative forcing analysis based on concentrations alone, you would have a bar for ozone. And that's what you have in the IPCC reports when they show the forcing relative to concentrations. But we don't emit any ozone. So we got to look rather at the precursors. So if you were to decrease methane, you would decrease ozone with benefits both for radiative forcing and also for air quality.
Is that factored into the new global warming potential estimates for methane?
In terms of global, I don't know actually. It is? Okay. I mean, I'll take your word for it. I'm a little, yeah, I'm a little surprised. Was that? Yeah, but I think that for global warming potential, it's not included, and it really should be. Yeah. So it's actually increased from 25 to 28. Oh. 34? Okay. I've got a little story on the increase from 25 to 28. That's actually has been implemented by the EPA in the last year. And that's simply because the CO2 radiative forcing efficiency is going down, because CO2 is being increasingly saturated in its absorption bands. So it's got nothing to do with methane. And again, a statement of why this equivalency between methane and CO2 causes more trouble than is really worth. Second question about the separation between sources. That's also a very good point. This is why we want to go to high resolution. So at the resolution that, for example, that Hannah Nesser did, she can look at individual landfills, when those landfills are isolated from other sources, when they are, within an urban area itself, then she has a very hard time. So we got to, some places are more difficult than others. In the U.S., for example, the oil and gas industry is very kind of separated from urban sources, so we can, but in other places, like in the tropics, oil and gas seems to be mostly produced in wetlands, and like in Nigeria and Venezuela, and it's very hard to separate the two. So we do what we can. We work with higher resolution. We use information from carbon isotopes. We do what we can. Yeah.
At least two. First one is, you haven't mentioned carbon-14 and the capacity to tell the oil and gas from everything else, oil, gas, and coal.
Right.
That must be a useful tool. But it can be used much. Second is, the OH, you said at one point, OH variability is minimal. How do we know that?
Mm-hmm.
So when you get these intermittent pulses, like the Turkmenistan pipeline, that leads to a whole implementation plan that's different from the one in the river system. Did anything happen when you told Turkmenistan that they had that kind of burst? Do you have any idea what caused it? The repair of a pipe or something like that?
We don't. Actually, looking for Daniel Veron, but he left the room. Actually, let me take your questions in order. So the first one about carbon-14 CO. Carbon-14. So carbon-14, the problem is that it takes a lot of air to do a carbon-14 measurement, and it's pretty expensive to do. So if we want to isolate oil and gas from other sources or fuel, we can look at ethane. And qualitatively, it will also be just as good. If we see elevated ethane associated with methane, that means that the methane is coming from oil and gas or coal, from some thermogenic source. With regard to OH being flat, this is, I didn't comment on that, but what we do in our inversions is we optimize OH concentrations so the methane sink at the same time as we optimize the methane source. And we find that there's some error correlation between the two, so we got to be careful. But we can separate them to some extent, and we see no indication that OH is really changing on the long term. There's interannual variability associated with OH, which we can relate to major fire years. But this is important because in the IPCC, they said that OH has been increasing by 20% over the past couple decades as a result of increasing NOx emissions. And we don't see this. And if OH was increasing like this would be even more difficult to account for the rise in methane. Because if you increase OH, you should bring down methane. Thank you.
Okay, well,
Okay.
thank you so much.
Thank you. Thank you very much.